Here we will see how we can derive the Jordan inequality. Is a famous inequality in analysis, and it states the following. That the sign of x lies between the two functions, the constant function 2 over pi and the identity function for x being in the interval 0 pi over 2. So I will give you an idea of how the function looks like. We know that for x0 sine of 0 is just 0, and for x equals pi over 2 sine pi over 2 is 1. So that's one part of my trigonometric function. So that one is y equals sine of x, and x lies between 0 and pi over 2. This part here, this line is y equals x. Y equals x times 2 over pi, because for x equals pi over 2 I get the coordinate equal to 1, and the other one is the y equals x. So for x equals pi over 2 I get is the identity mapping, I get pi over 2. So the graph looks like this. How do we prove this inequality? So how do we prove this inequality? Let's start with that part. We set h of x equals sine of x minus x. So I prove first that sine x is less than or equal to x for x belonging to 0 pi over 2. I need to work two parts of the inequality. So I take the derivative to find the monotonicity of the function. The derivative of sine is cos, and the derivative of x of the identity function is just 1. So x is between 0 and pi over 2. Cos x is a decreasing function on that interval. So I flip the direction of the inequality. So let me rewrite the inequality. Cos x is greater than or equal to cos pi over 2, less than or equal to cos 0. That is 0. So cos x is between 0 and 1. Now take away 1. I have minus 1. Cos x minus 1 less than or equal to 0. So that part here is my derivative. H prime is less than or equal to 0. So h is a monotonically decreasing function for every x in 0 pi over 2. So that means that when I pass h, I have to change the direction of the inequality. So my h of x lies between h of pi over 2, h0. My function h of x is sine x minus x, and the h of 0 is just 0. And from here I have sine x less than or equal to x for every x in the 0 pi over 2. So I have proved this this part of the inequality. So I have dealt with this part. Now I have to deal with that part. So it's an x here. I have to deal with the other part of the inequality, which says that 2 over pi times x less than or equal to sine x. I can I can polish the inequality, so I have 2 over pi less than or equal to sine of x over x. Then I can define the function p of x equals sine x over x minus 2 over pi. This is the trickiest part here. I have to calculate the derivative of this function using the quotient rule. So let me rewrite this function as 1 over x squared times m of x. I cannot determine the sign of the function. I cannot determine what is if the p prime is positive or negative. I cannot say from here. So I have to compute the derivative of the function m. So I have to use monotonicity here. So I calculate the derivative of this function. So I have the derivative of that. I use the product rule for the first term, and the derivative of sine is just cos. What did I do wrong here? Oh, nothing. So that is minus x sine x minus cos x, and then these terms vanish and I have minus x sine x, and this is negative. I can prove that. Let's do some working out on the side. So x sine x is positive, so that quantity is negative. So it means that m is a monotonically decreasing function. Is a monotonically decreasing function. So for x between 0 and pi over 2, m0, I flip the direction of the inequality. So I have mx greater than m pi over 2 less than or equal to m of 0. The m of x less than or equal than m of 0 is 0. So that is negative. So I go back here. This whole thing is less than 0. So from here, p is a monotonically decreasing function for every x in 0 pi over 2. So I have x 0 pi over 2. My function p is monotonically decreasing. So I have p0 greater than equal to px greater than equal to p of pi over 2. So my p of x is greater than p of pi over 2. P of pi over 2 is 2 over pi. I just rearrange this, I just brush up the inequality, and I have 2 over pi times x less than or equal to sine of x for every x in 0 pi over 2. This part was a little bit more tricky. There are other ways to prove Jordan inequality is using geometry. You can prove it visually, but here I tried to use analysis techniques, monotonicity properties. The first bit, so to prove the first part here, it was straightforward. The second part, that part here, I need to take the derivative of this function, and then of course 1 over x squared is positive in for every x 0 pi over 2, but I don't know what is the sign of this quantity here. So I define a function m, this function to be m. I take the derivative of this function. It's negative, so m is monotonically decreasing, and from m monotonically decreasing I find what is the sign of the function m. Once I find the sign, I find the sign of the whole thing, which is negative. The derivative of the function defined before is negative, so p is a monotonically decreasing function for every x in the interval 0 pi over 2. And then using that, I can just pass the function, but I have to change the direction of the inequality, and I get the desired result. The second part is again a little bit more tricky to prove. It's a two-sided inequality, so to prove the left member of the inequality is a little bit more tricky. But I mentioned this inequality because it's very famous. Jordan was a very strong mathematician, and this is a ubiquitous inequality in analysis.